So we've moved on to part C of our work and friction problem, and part C says that we soon meet an incline of 15 degrees 6 meters in length as we're pushing this box. And we want to know how much work changes if you apply the same force up the incline. So the same force as before that we've been pushing this box, 350 newtons, is still being applied as we are pushing up this ramp. So we can just quickly draw a free body diagram of this situation so we can get a good sense of which forces are going to be applicable when we calculate our work. So we have the surface of our ramp, and then we have our box, and of course we are pushing this box up the ramp, so this direction would be our push force. And then as we go up the ramp, we have gravitational force pointing down toward the ground. What a horribly unstraight line. But regardless, our gravitational force pointing down. And then we have our perpendicular component of gravitational force. And then that points into the ramp. We have our parallel component of force, and then we have normal force, which we'll do in the same color as perpendicular force because that is equal in magnitude and opposite in sign to the perpendicular force. And then of course we can't forget that friction force is still acting against our movement even up this ramp. So with that coefficient of friction of 0.6, in the same direction as the parallel component of gravitational force is our friction force added on to that. So with that, these are all the forces acting on our box, and we need to decide which ones we need to count when we calculate work. So of course we're going to ignore this gravity vector because we split it up into its components, so that doesn't need to be counted. But we have the perpendicular component of gravitational force and the normal force, which are equal and opposite to each other, as we said before. So these are actually going to cancel out, and we don't have to worry about either of these when we're calculating the work. So with that, we're left with friction force, the parallel component of gravitational force, and our pushing force. And we just have to hope that these two forces acting against us aren't greater than the force that we're applying, or else our box won't move up the ramp. So we just have to write out that our net force is going to equal, and then we have a positive push force of 350 newtons, and then we have to subtract the friction force, the F friction, and the parallel component of gravitational force also subtracted. And then after we sum all three of these, we can just go straight to our work equation. Our work is equal to the net force times our distance, and our distance is just the ramp length of 6 meters. We actually have the word height here, but that's not right. It's the ramp length is 6 meters. So we don't have to worry about doing the triangle stuff. No trigonometry there. But we will have to do a little bit of trigonometry to get our friction force and our parallel component of gravitational force. Because we are sitting on a ramp, and at this angle our friction force has changed because our normal force has changed. So that's the very first thing we're going to worry about. So the very first thing we should remind ourselves of, and we talked about this in I think weak to where we had that other ramp problem. When we have the gravitational force downward on a ramp, we have it split up into its parallel and its perpendicular components. And we have the angle of the ramp, which is by like triangles translated here. And so our parallel component is going to equal our gravitational force times sine of 15 degrees, and then our perpendicular component will be our force times cosine of 15 degrees. And we just have to reapply this when we're calculating these two forces here. Because first of all, we know that friction force is equal to our coefficient of friction times normal force. And we said earlier that our normal force was equal and opposite to the perpendicular component of force. And we said that that was equal to mass times acceleration due to gravity times cosine of 15 degrees. And then as well, our parallel component of force was mass times acceleration due to gravity times the sine of 15 degrees. So from here to calculate the net force, it would get pretty long to plug in all these numbers. We could, but just to save time, we're going to skip that because we know that the friction coefficient is 0.6, our mass is 40 kilograms, and we know acceleration due to gravity. So 350 minus all of this multiplied together minus all of this multiplied together is going to equal a much smaller net force than before, and that is going to be 21.02 newtons, which is significantly less than the previous parts. So we are just going to plug in this net force into our work, and this is going to equal work. It's going to equal 21.02, and then we've just been pushing this box along the entire length of the ramp, 6 meters, so that is simple enough. And this 21.02 times 6 is going to equal a work of 126.13 joules. So this is much, much less work than we could have done if we ignored friction, but we still had to have accounted for the parallel component of gravitational force. But regardless, this is the work that it takes to push the box up the ramp, and with that, our work problem is done.